great to be here, and thanks for the invitation. It is quite special even for me. The summer school is especially it's not a workshop, it's not a conference, like a workshop, summer school. So it also gives me more pressure to give 2-hour presentation. So before I start my presentation, I will share some of my own experience and also our group. For who don't know me, so I'm Shan Luo. I'm leading the Robot Perception Lab at the Center for Robotic Research at King's College London. And our lab's name is Robot Perception Lab. So everything related to robot perception, so that's what we work on. So it also means we not only work on like tactile sensing, but also we work on computer vision. So this is related to my own research interest. So I have got most of my research in the field of tactile sensing. But also I studied my Ph.D. When I was at King's as a Ph.D. student. I got some interest in computer vision as well. So from there, I got some idea to apply computer vision techniques in the field of tactile sensing. Okay. So that's how I developed the research plan in tactile sensing and also in computer vision, and then we got this robot perception. Okay. So in this talk, I will focus on tactile robotics. So from sensing to perception and also to action. So perception is the core. So we need the hardware, and then we have software, and we have the the simulations and evidence. And also because of the interest in computer vision, I attended the International Computer Vision Summer School in Sicily quite a few years ago, and I got the impression what you can get from a summer school. And one reporter told me, okay, hey, we're planning to organize one summer school for tactile sensing, and I was quite excited. So I'm here, and I'm quite excited to share what I have got over the past year with you, the future stars in the field. Okay. So this is me, and this is our lab. And I will show you some inspirations, and then I will delve into some reasonable works in our lab. We always get the inspirations from humans. So we call it tactile intelligence in some sense. So we always say artificial intelligence. We have seen many intelligence forms in computer vision or in NLP, large language models, and now tactile intelligence is emerging. So it is involving robots to have the sense of touch, and then we can have intelligent behaviors in robots. Then we have these inspirations from human. We use our multi-modalities, vision, tactile sensing, in performing these tasks. So here are some examples. So when we do laundry, we use our eyes. So you can see here we use our eyes to have a glance of these clothing. And we can capture some key points of these clothing. And then we know which points we can touch on these clothing. And then we can fold these clothing through our actions. So this is the folding, this is the laundry task for us in our data. Also for the sewing task, so you can imagine you are using your eyes to pick up where the needle is, where the cloth is, and then the eyes will guide the motions of the hand, and the tactile sensing at the fingertips will give you more information of the needle, the cloth, and then you can perform the task. So these are the inspirations. That's what we do in our data. And then we have seen some research work. This is the famous one. Probably everyone has seen it if you are interested in tactile sensing. I don't have to go through the details. So basically, the human subject loses the sense of touch as the hand is undersized. So that's why the subject cannot feel the sense of touch at the fingertips. And then the subject cannot perform this simple task of stretching a match. Definitely, there are many discussions around this experiment. So people may see it not only tactile sensing, but also kinematics, prior perception. But from the result, you can see without tactile sensing or without kinematics, it's very challenging to perform the task using one single modality, that is vision. Yeah. So the subject is seeing match and performing the stretching action using vision. Okay. So from there, we have got the research plan into hardware simulations and algorithms. And then the very first thing we have considered is what sensor we can have for robots. So we have seen these tactile sensors for visual for tactile sensing. And from the human tactile sensing, there are some studies to look into the mechanical receptors in fingertips. We have around 200, more than 200 molecular receptors in our fingertip. So that's the number of the mechanical receptors in this area. And then we have seen different transduction approaches. So in the morning, we have seen different transduction methods like optical ones, magnetic ones. So your skin is one of them. So it's magnetic. You make one single sensing element to sense the pressure in that point. And then you arrange the sensing points in one planar surface or curved surface, and then you can get the tactile sensing. So here, here's the concept of tactile sensing. So that's distributed. So it's not only the force of torque sensing in one point. But for such sensors, for your skin, you can only make like 20 or 30 pixels. So we call it tactile elements or tactile pixels for these sensors. The maximum number they can get is 20 or 30. That is much less than what we have in our fingertip. Okay. Another example is the bell tag. So we can measure these physical signals through these sleeves, through the normal force. And for this one, for bell tag, we have 24 pixels around the finger. Around the finger. I see Catherine.
It's 19.
It's 19. So, 5, 9.
It doesn't, I mean, there are only 19 electrodes. And
Okay.
It doesn't matter.
Okay.
It doesn't.
The traditional Biotac, the newest
one
version
that's
at
shown-
21.
Okay, maybe it's 21, but it's not 24. It doesn't matter. I'm sorry, I shake my head when I hear something that I think is wrong. I don't mean to.
Okay. Yeah.
You can count them
Yeah.
yourself right there.
Yeah.
I was just doing it.
So for my practitioners,
It doesn't matter.
in my lab, I didn't get the bell tag in my lab, so that's why I didn't. So that's the number I got from the literature, but later we can have some discussions. Yeah. So bell tag is similar to your skin. You arrange these electrodes for each sensing element, and then you can get like 19 or 20 something pixels for the fingertip. And there are many other sensing principles, like capacitive or piezoelectric, piezoresistive, optical, thermal effect, ultrasonic. Stefan has given a very good overview of these sensors in the morning. I will not give more details in these principles. And there's some other applications. For example, the surgical operations. So minimally invasive surgeries. That's another example of beyond the fingertip. So here you can see if it's open surgery, so the surgeons can feel the tissue and then can tell this is tumor, this is normal tissue by differentiating the stiffness of the tissue. That's what surgeons usually do in open surgery. If you have the minimally invasive surgeries, you have the shoulder pulse, and you have a small hole in the patient hole. And then you insert the surgical tool to observe the space of the patient hole. Usually you have this surgical camera to see the inside. However, it's not possible to feel inside, like the open surgery. So that's why if you have the tactile sensing inside the body at the two sides, two tip, and then you can capture the pressure distribution at the tip. And then you can tell this is the tumor tissue other than the normal tissue, and then you can do the surgical operations. So these are the examples of different sensing principles and also some applications. So for our research, well, for most of them, they are task-driven. So we identify a task, and then we define our tactile sensors, and we find the suitable sensing principles for this task. I will give you some examples. And then this comes to the vision-based tactile sensing. Stefan has already given a brief introduction to this approach. I would like to recap the sensing principle of vision-based tactile sensing. So for vision cameras or vision sensors, we have RGB camera or depth sensor. That's what you can have from camera and the laptop camera or the camera from your phone. And the raw data you get is something like this. Okay? And then you have intensity, the values in each pixel. So this is how you form an image. Okay. And then from this pixel, the intensity, you can tell the features of the visual information. So from here, you can probably tell this is a picture of Lincoln. That's how you do sensing and perception from vision. So this is the vision part. And then we apply this vision sensing approach to tactile sensing. That's how we get vision-based tactile sensing or vision-based tactile sensors. So one typical example is gel side. So there are few key elements. So we have a camera in place, and we have a few LEDs to illuminate the space. Okay. And we have a soft elastomer on the top. So it has one layer, one transparent layer to transverse the light, and also it has a reflective layer on top, so that we can reflect the light. And when the object is interacting with the elastomer, the camera can capture the information of the elastomer. Here's one example. When you press your finger against the gel side, you can get the texture of your fingertip. So basically, you can do a fingerprint from the camera vision sensor. Also, you can have these black markers. The black markers can give you more expensive motion of the soft elastomer. Okay. And then by tracking these markers, you can get shear force or normal force from the markers. So there are some advantages of vision-based tactile sensing. Spatially, it's high resolution. Okay. So from the previous slide, so you may recall for the fingertip, we have around more than 200 sensing elements. For vision-based tactile sensing, you get a high resolution in nature because of the camera you use. So you get the camera resolution for the tactile sensing. So you get millions of pixels. So it means you have millions of tactile pixels as well. So from there, you can get very rich information. You can get texture, like the fingerprint. You can also get force, like shear force, normal force, from the subject. And also, on the other hand, it's natural for visual tactile integration. So in nature, it's data from camera. So it means you can apply vision-based techniques to process the data from vision is tactile sensors. And also, when you integrate the vision and tactile sensing for perception and manipulation tasks, you can pursue this data into your network and in the same way as they are the images for both of them. So that's why it's easier to process such data. So here you have seen some backgrounds of various tactile sensors that we mainly focus on in our lab. But in the next, I will also take actual aspects of the landscape in tactile robotics. So this is a paper that we have accepted at attribute transactions on robotics recently. It's called, the title is Tactile Robotics Outlook. We brought this paper as tactile robotics as we believe tactile sensing is important to robotics. So sensing, perception, and also actions run on tactile power. So that's we brought it as tactile robotics. There's another paper over 10 years ago from Ravanda Takia. It's tactile sensing from human to humanoid. So after around 10 years, we have summarized the trends in the past years, and also giving an outlook for the next decades. Okay. So here we have outlined a few key areas that we think that will be of interest to the whole community. So we start from the sensors themselves. We have the artificial tactile receptors. So this will be related to materials, for the skin, for the transduction, and also we have the tactile sensor distribution. So that is the sensor network. We have seen many works only focusing on fingertips, but it's also very important to connect the sensors all together as a network. So this is similar to us humans, as tactile sensing is not only in fingertips, but across our body. And they form a network that you can make your decision based on the information across the body. But then, once we get the data, we have the data processing. So we have seen approaches in using neural networks or traditional methods. Also, we have seen the recent trends in simulations. So you can collect the data in simulation, train your robot agents in simulation, and then you can transfer such agents to the real world. So that's why this has gained a lot of interest in the field, tactile simulation. But here I would like to highlight tactile simulation can mean something different. Right? So for psychology, simulation can mean like imagination through your tactile sensing. So you can imagine what will happen in the next with tactile sensing. So it's more like an engine, so you can predict what is the future if you have gained a lot of data in the simulation. Now we have seen different repetitions of such data. We have seen like tactile images from the various tactile sensors. As we mentioned, in nature is an image from the camera. So that's how we call it tactile image. Also, we have seen this tactile data from the arrays. So in such sensors, you arrange the sensing elements, either a plane or surface, and then you have these arrays of data. Then we have seen these waveform signals, like tactile whiskers. You get the vibration signals, and that's how we have the waveform signals. Okay. Now we have seen different applications. Manufacturing, automation, and manufacturing. Also, we have seen minimally invasive circuits, and we have seen warehouse automation, recycling, laboratory automation, and agriculture. So these are the applications that tactile sensing can be useful. Okay. So this is our outlook paper. we asked a few research questions to the community. So, because I know many of you are first-year PhD students, and if you are looking for any research questions for a PhD, so this may be useful for you. I will show some of them in my presentation. Okay. Many of them are still open questions. We don't have an answer yet. So I personally learn a lot from the community, and I'm learning every day. So these questions I don't have an answer either. So at the end of some of the sections on the presentation, I will ask these questions. I would like to hear your thoughts. Okay, that's how I call it Tactile Hunt. Okay, so through my research journey, it's more like a treasure hunt. Through publishing the works and communicating with the peers, so I have seen some treasures in the research field. So to you, as in the coming years of your PhD, so it's also more like a treasure hunt. So these research ideas, research works can also be taken as treasures throughout your PhD. So I will throw out some questions in the presentation. Okay. So in the next, I will share some of our research in 3 sections. So the first one is on hardware, so on various sensors. And the second one is on simulation. So how to generate synthetic data. The simulation can be through a simulator. It can also be through data generation models. As an end for the processing, so we have repetition learning. Also, I will connect it to like reinforcement learning. Okay. First of all, we can see some hardware. So for the following works, I would like to group these works into different schemes. Now I will start with rubber fingers. So that's the most common we have seen. So we developed some sensors that in form factor similar to a fingertip, and then we equip these rubber fingers with such type of sensors. And then I will share some other sensors for different applications. The very first work we have developed in our lab is called gel tape. It's the first all-around high-resolution tactile finger. The sensing principle is similar to the gel side you have seen before, but it has a different form factor. It is more similar to a finger, even though it has the name of gel tape. Okay. So it has the same key elements as the gel side. We have a camera at the base, okay, from here. And we have really supporting layer here that is also transparent. Transfers the light. Now we have a layer of transparent elastic. Okay. And on the surface, we have the reflective group to reflect the light. So that the light can travel through the space. And then the camera can capture the deformation when one object is interacting with the finger. Okay. And this is the sensor prototype. This is the 1 pound cone, so you can see the size of the finger. And here's one example. We use our gel tip sensor to equip one gripper. So there are 2 sensors on both sides. And then when the sensor is grasping one strawberry, you can get the detailed texture from the sensor. Okay? So that's how you get the high resolution sensing. And here's a quick demo to use such a sensor to to detect the contact around the finger. We have a 3D printed object here, and we use the gel-tip sensor to tag the 3D printed objects from all directions. So from the outputs, we can detect the contacts with the objects. So around this finger. So the way to have all-around tactile sensing for the finger can be useful for like unstructured environment, and the contact can be from anywhere. So not only from inside the glass. So from any other literature, you can see many of these sensors are designed for the grasping, for the sensing within the glass. For this design, you can get sensing from the inside, from the tip, and also from the back. So all around the finger. So that's the very first prototype we have got for vision-based tactile sensors. And then we have developed a few other sensor prototypes. The recent one is called Ph.D. So that's a sensor with cross-modality interpretation. So here, cross-modality means we have vision and tactile sensing. So vision is a proximity sensing. So when one object approaches the sensor can detect there's an object approaching. And then we have tactile sensing, similar to the gel tip or the gel sensors we have seen. Here we have got this camera base, and we have the sensing tip. So that's similar to the one you have seen. But the tip is a bit different. So here we have the markers. So we have these black markers on the tip. And then when we have the indenter, when we have this object, but it gets in contact with the object. So we will have some space, the soft elastomer. And then the camera can capture the deformation of the elastomer. So this comes to two challenges. So when the object is approaching the sensor, we will have the vision sensing, these black markers will be noise to your perception system. So here we have to remove these black markers so that we can get a better proximity sensing. So that's through this processing, data processing. Then when we have this contact with the object, if we get the texture and stiffness, so we also need to get the force sensing from the sensor itself. So that's how we have get the shear force and the normal force. And here is the architecture of the Ph.D. sensor. So as you can see here, we have a layer of the markers. And then by using these markers, we can differentiate proximity sensing and also these tactile sensing capabilities. So here's a closer view. So you have these markers with this pin and these black dots, and also you have the lens here. So here is one example when the sensor is approaching this object. So you get this profile of the object, but you can see you have these black dots, these pins, and then you need to remove these pins to get the profile of the object. And then when you get these contacts, so the markers are moving, and then you need to get the force. So here we have got these computational models to process the data so that it can maintain these two modalities. So here we have got these generative and adversarial models. So we track the data for both proximity sensing and also the tactile sensing, and then we take the other modality as our ground truth data so that we can learn how to remove such markers. And then we can clean up our results so that we can get these proximity images without these markers that you can see here. So then you can get these real features. And then here, when you have these tactile sensing parts, you can extract these markers themselves, and they are more representative of these force, and then you can get tactile features. So you can separate real features and tactile features through these computational models, and then if you need, you can combine these real and tactile features through another model. So here are some results. So here on the top, these are the original image. So you get these strong white areas. So when the sensor is approaching this object, and then you can remove these black markers so that you can get better profiles of these objects. So you can see these different shapes of these objects. And then here for tactile sensing part, you can remove the lights and then you can skip these markers. By tracking the motions of these markers, you can share force and normal force.
Shan, do you ever thought of it, because you have an LED ring, and that's to illuminate the markers from the inside. Do you get a useful image if you turn the LED ring off? I'm just thinking about like a sort of background subtraction method where you turn it on, turn it off, look at the difference. Would that be useful to discriminate the markers from the outside image?
Yeah, you mean the ambient light.
Yeah, like the ambient light might look the same in both images, but the markers would be like maybe brighter and darker. You could figure out which is.
Yeah, that would be a good idea. We haven't tried this before, but I'm thinking probably you may be subject to the noise in the ambient light, as you may have different light sources, and then these light sources can affect the light diffusion of these markers.
Yeah, I have no experience with that. I don't know what kind of images it gets. That's why I was wondering what would it look like if you turned the light off. So.
Yeah. Yeah.
So you're pressing different objects onto the sensor for this software. And are the objects all white, or is that just how they appear? So I thought you guys were planning to have a completion sensor to get the RGB quite precise RGB values.
So for this one, we just used the white light. We didn't use the RGB. But for your question, you mean the colors of the objects? Right? Yeah. So for this one, we used the white materials. But we had these 3D printed objects. So that's why these objects are in white.
But it works for all.
Yeah, but it should be able to work for all.
Question. Instead of using sort of this machine learning approach, would it be possible to do this optically by just changing the focal length?
That should be possible. I've seen some works. So one way is you can have a special pen, and then you can use an infrared camera. And then when there's a contact, so you can so the infrared camera can detect this contact. So you can turn on the sensing or off the sensing. But there will be a delay as switching on, switching off, depending on the pen itself.
Because so there was also this work from Canada where they had this paint that was basically depending if you were projecting light. If you were projecting light, it would reflect it back. But in the moment when you were turning off the light, then it would be transparent. A little bit like these security glasses.
Yeah.
But in this case, since you are anyway always transparent, what you could do is just that you could manually change the focal distance so that if you focus on the marker, everything behind is out of focus, so you don't really see it. On the other side, if you want to now see through, you just basically put your markers out of focus so you don't see them anymore.
Yeah, so in that case, you have to tune the focal length.
Right.
For example, for the tactile sensing, you are always in this part, this distance. But if the object is approaching, you need to set up a threshold to see this in this distance. I think it's also possible. I think it's a good idea.
It's mechanically a bit more complicated because you typically want to have a motor
Yeah.
in the lens,
Uh-huh.
but otherwise it might be
Yes.
useful for you.
Yeah. So we did try some of these cameras with tunable focal length, but from our own experience, they're not very reliable. Yeah. So for our sensors, if you have tunable tactile like focal length, it'll be easier to detect the deformation. Yeah, but from our experience, that it doesn't work very well.
Okay, interesting.
And here's a quick video to show the sensor. So the second chamber will print in what? So the previous one was another semi-type prototype we have almost. And the more recent one we have all these the rotate balls. But as I mentioned, we really is task driven. So for this work, we aim to address handling thin and flexible materials. So they are very common in our daily life, like book, so how to flake a layer of book. Or in manufacturing, you have the flexible composite. So it's also very common in manufacturing. And all if you count your money. So it's the same problem. Okay. So here the aim is to flip each layer, and then you can count the number of layers in the gripper. So before this work, we have done a lot of literature review, and we haven't seen any robotic system that can perform this task. We have seen some software grippers that can grasp several layers of these materials, but we haven't seen a gripper like this that can feed each layer to the gripper and then count them. So, inspired by this task, we have designed this sensor called rotate, and then we designed this robotic system called rotate ball. It's similar to the gel tape you have seen before. So the tape is the same as the gel tape and the body. But the main difference is the rotation mechanism we have attached on top. So the gel tape sensor can rotate. And then with this rotation, you can leverage the shear force to phase each layer of material into the center of the gripper. And also through the tactile sensing, you can count how many layers you have got in the gripper. So here is a view of sensor. Similarly, you have got one camera, you have the elastomer, you have the reflective layer, but here we have got more function. So here the sensor itself can rotate. So here is a compressor. So as you have seen, as I mentioned, so for software clippers, they always grab one layer each time. Or if you use second cuts that are common in the industry, so it can always have one layer as well. But for our approach, you can grab several layers and fit them in the center, and then grab these layers of the materials.
Shan, the bottom row that you have there, is that something empirically verified, or is that just sort of like schematically what you think is true?
So I mean, this two.
Yeah, are they? Did you empirically verify that like E and E is always true, or is that something you hypothesized?
So these two, we have seen them in the literature. So not from our work. Yeah. So there was one work from University of Technology, Shan Technology. They developed this software paper to grab different layers. And we have seen their experiment for each time, and we can only grab one layer. Yeah.
It just feels like I could probably come up with a suction cup design with two suction cups that would do the same thing as yours. It seems like a little bit. I was just interested to see if you'd actually empirically verify that it would be impossible to do the suction cups as software, for example.
Okay. So you mean, how can you handle several layers?
You go one by one. You go suction cup on the corner, you flip, and then it gives you the suction cup. Just flip like you do with your hands.
But how do you hold this layer together?
How do you hold?
Hold the air. So if you pick up one layer, and when you put the next layer, how do you hold the previous layer?
Hand. So you can suction cup for this one.
Oh, okay. Yeah, so that's the difference. So for the second cup, you pick up one and put it aside, and you pick up another one. But what I'm highlighting here is you need to pick up several layers and put them in the center of the paper. You are holding several layers. So you can imagine if you count your mind, so you're using hand and you're putting several layers in between these two fingers. But what we are saying is you pick up one nose, put it aside, and put on one nose, put it aside. But it's not what you do when you count your mind.
How common is this? How common is this work?
You mean,
Yeah, counting money. How common is it?
Yeah.
Like, what are the applications of it?
so we have seen some applications for like assisted robotics. So when robot is assisting an elderly or disabled, so the person can ask, okay, you flip to page, turn to page 15. And also in manufacturing, we have talked to people in the industry. So they are quite interested in this, as when you do this composite manufacturing, then you can count how many layers you can get, and then after you count them, you transport them to another station. And so that's the application we have seen for this work.
Thanks.
Maybe it's another question. So this is just for parallel draw workers.
Yes.
Yeah. Imagine once you have 3 fingers.
Okay.
Think,
It is possible. Actually, that's what we are doing now. Yeah, that's what we are doing in lab. So we are flipping this mechanism to a level hand. So that's a 4-finger grip, 4-finger hand. So for each finger, we have one this rotate sensor.
So I guess maybe the question is, once you have the additional fingers, I would have thought you wouldn't need the rotatable system because we don't have, I guess, biologically, we don't have rotatable systems in these companies.
Yes, yeah, that's true. It depends on so there are 2 sides. So one side is the task space. How many degrees of freedom you need, and which degree of freedom you need, that's the task side. So what we do here is on the robot side. So we basically we add one additional degree of freedom to the robot figure. So from our case, so we are developing this robot for some specific applications to meet the additional degrees of freedom in the task space. So that's why it depends on what task you're working. Yeah.
I guess maybe following up on that question, just out of curiosity, if you were to speculate, is it better to have like 2 fingers with like rolling, 3 fingers with rolling, 4 fingers with no rolling? Like, what is like the optimal design for general purpose robotics?
Yeah, that's a good question. Yeah, so we have been talking to our colleagues who work on pneumatics and the dynamics, and there's some theory to prove so it's an optimization problem. So you have the morphology of the hands, you have the degrees for each finger, and you have the task requirements, and then you can work out what is the optimal number of degrees of freedom in your robots.
Sure, but what do you speculate? Give a number.
Okay, so for this task,
Not for this not general purpose robotics, like you want something to work right in your home.
That's hard to say.
Fair.
Yeah, so I would say that's similar to the human hand, around 100. But I would say there is one good example to answer this question. When I went to Berlin, there's one museum of technology there. I have seen this one demonstration of a hand with additional finger. So that is the human communication. So similarly here we are doing like robot augmentation. Usually we have a parallel gripper and we are augmenting this parallel gripper helped by this additional degree of freedom.
Thanks.
Here, I'm going to show some demo videos with our robot here. So this is what I mean. So you can count different layers, and then you can hold them together in the center of the robot. And we have also showed the capabilities of the robot in performing different tasks. For example, you can rotate this arrow key, you can rotate this count. And this is the cable pulse estimation task, as you can see here. So different from what we have seen here, for here, we didn't have any markers, and we only rely on the segmented error, the counted error, to know the counted base. Then we can do the repeat. But here, see, we have added markers to the sensor as well. And then we can get the force, and we can estimate the force.
So including shear, I mean, that's what I'm getting at. Can you actually determine the torque?
So for shear, in series, yeah, you can get all from the motion of the markers. And also we have showed generalization experiment. So here we are showing this fabric handling task. So the robot is handling several layers of the fabric. Next, I will show some of our other prototypes briefly. They are not very important, but we have shown they are working in different areas. So one is at large scale. I'll show you what it means. So for infrastructure inspection, so usually they have large areas. So these human workers, when they inspect these infrastructures, they not only use their eyes or they use devices, but also they touch the surface. So one aim we have is to use robots to inspect such infrastructures. And such infrastructures can be dangerous to human workers. At bridges or these underground, sometimes they are very challenging for humans to get into. And then, so for this task, we have developed these robots that can inspect such surfaces more efficiently. So for this task, we have two simple prototypes. So one is called gel finger. Here we have all the same elements: camera, elastomer, reflective layer, but the camera it can be rotated inside the sensor. Then in that case, you can stitch together several images, and then you can get a large area of assessment. So that's the key idea of the gel finger sensor. So as you can see here, when we have a contact, the camera can capture several images. So it's looking at this part first, and then it will capture this area, and then it will capture this area. And then you can stitch the expected images all together, and then you can assess the whole area without moving the tactile sensor. So this is also motivated by our observations with gel cell sensors. If you have a large area, and if you use the gel cell to assess such areas, you have to tap each area and then lift the gel cell sensor and move to another area. Okay. But for here, we are just rotating the camera itself, and then we can capture several images. And here we use pseudo crack so that we can capture several images. So this is one single touch, but it's capturing several images. This is scanning this touch area, and then you can stitch around it. So then it turns into a computer vision problem. You get several images and then you stitch them together. So this is the image stitching problem.
Is the camera moving or is the finger moving?
The camera is in the camera inside the sensor is moving.
But the finger stays stationary.
The finger stays. But later we'll have another prototype that shows the sensor is. Here is a comparison. So we have the gel finger with different variants. So we have different field of view. So this is root days and this is days, and we compare to gel side. So the field of view will be the same, like 60 degrees. But for gel side, it's a fixed angle. So by rotating this camera, you can get much larger detection area. So we can get 15 square centimeters compared to gel side of 1.5 square centimeters. And then you can apply this image detection techniques. So here you get a bunch of the images, you get image stitching, and then you apply these computational neural networks, you can segment these cracks in the image.
Do you have to fine tune that model, or does it just segment out the cracks?
But we need to thank him in ways how we do.
How did you get the data for it? The track data, I assume you have to have segmentation masks to label. Right?
Yeah.
How did you get those?
So we have to manually annotate the data.
How did you do that?
So from our experience, a few hundreds or few hundred, yeah. And this is another example I have got for rolling assessment. So for this task, the sensor itself, the camera itself is fixed. It's always pointing down. Okay. You can see it's attached to a UI5 arm, and the camera is always looking downside. But the elastomer is rolling. The shell of the sensor is rolling. So here you have a large area of fabric. So they have the indication that when you roll over the fabric, so you get this tactile image. And again, this is image stitching. Here, the camera is not rotating. The shell itself is rotating. Then you can stitch them together. You can get a global view of this fabric. Okay. Another application we have been looking into is minimally invasive surgeries. And this is also the task I got when I started my Ph.D. When I started my Ph.D., so many of my lab members were working on surgical robotics, and they were working on tactile sensing for surgical robotics. So that's how I started. But to that time in 2012, so there was not much research in really this tactile sensing. Okay, so we were looking into different approaches, and we have been looking into optical tactile sensing, capacitive tactile sensing. So here I'll give you my story. So, and I'll show you how I started the research in that area and how I picked up again Dresden. The motivation is to give surgeons the sense of touch for the inside of the patient. So normally this is the view you can see, so the surgeon will see. It's quite blocky. You have the surgical tool, and the surgeons are sewing these tissues, and usually these verrucles are blocked by these tools, bleeding, or anatomical geometry. It's very challenging, and when they do sewing, you can't get any haptic feedback. So they don't know whether it's successful, whether there's any treatment change from the fluid. Okay. So it means if there is a failure, it will result into harm to the patient. So that's why we have looked into applying sensing, tactile sensing in surgical applications. So Da Vinci is the modern technology is developed by a surgical company, Da Vinci, and it has been very successful in the surgical applications, and they have been used in many hospitals. However, even though there is a lot of research in tactile sensing for surgical applications, only recently, in 2024, they applied force sensing in surgical applications. Yeah, so you can see that's 12 years later after I started my Ph.D. Okay. It was a very challenging task, as you can see, it's quite bloody, and it's very challenging to miniaturize the electronics and put it in the patient body. Okay. So the last year they had released their product, and they can sense the force sensing at the tool tip. But here, this is only force sensing, 1 point. You get a force value at the tip. Okay. But on their website, they're claiming so surgeons with varying experience levels can deliver up to 43% less force on tissue by sensing the push and pull forces the instrument tip through force feedback. So the thing is, with tactile sensing and force sensing, it can be useful to reduce trauma to the patients.
And this is my naivete just asking, but like, were they applying like unreasonable amounts of force and 43% is like meaningful, or was it fine? Like the force that they were applying anyway was okay, and now they have a 43% reduction on something that was not a problem anyway.
My perception is that they didn't have the data. They didn't have such data before, as they didn't have the force feedback or force measurements. Here, they got some operation studies. If you have the force feedback, so you're applying less force. That's the metric they're using. So it means, so their logic is less force to less feedback. Especially when you have the vessels and you have a lot of blood, and if you apply too much force, so you may cut the whole vessel, and then there will be a tragedy. So that's why they want to minimize the force.
I'm just kind of curious if they have statistics on how often these surgeries go wrong.
We have been talking to doctors at St. Thomas Hospital and Gas Hospital that are associated with Hospital of Kings. We have been talking to these surgeons, and they have been telling us this is very important, but there's no such literature. There's no doctor who will say, hey, if I apply too much force, if I don't have a hospital bag, I will fail to do this. They know this is important, but this is not relevant in the literature. We have searched very much literature, but we haven't seen a statement to show that. But we have heard from the doctor to say that okay, tactile sensing, force sensing is very important.
I wonder how, I mean, it could be anecdotal as well. I mean, I had one conversation in this area and I decided not to go there, but it was with a colorectal surgeon and I'm sort of selling it to him. You know, tactile sensing could be great, you know, okay, let's get on board. And he was like, I'm really good.
Yes,
I'm really good.
You didn't know to say how good.
It's not the experts who need the haptic feedback, it's the new surgeons. Don't
Yes.
be the one, don't be the first 20 patients of any surgeon operating with the Da Vinci, because they have to learn to operate with
They have
only
to
sight,
push
unless
the
they're
button.
using the new robot that has some haptic feedback.
Yes. So they are very reluctant to learn this new skill. They have been trained to do this operation without haptic feedback. So they see the views, but they don't have the haptic feedback. But they told me if you have the haptic feedback, they have to adjust themselves to the new haptic feedback. This may not be accurate, this may not be good enough. So that's why they are not willing to get haptic feedback.
Yeah, I've got anecdotal evidence as well to support that. With the family members who have surgery, the surgeon would just say the bowel particularly doesn't like being touched. So even, which is counterintuitive, you might think you can just touch our organs and it's grand, but even like contacting our organs, like they're not supposed to be contacted, it can have very unintended consequences. That's just my 2 cents.
Thank you for sharing. So here are some views. You get the soft tissue and the vascular grasping, which is very common in these hip surgeries. And here, for force feedback, the assumption is that so if there's a tumor, so the stiffness will be different, especially for breast surgeons or prostate surgeries. So force feedback is soft tissue grasping, but it's insufficient to capture complex information. So that's why we claim we need tactile sensing for surgeries better than force sensing. So this is back to 2016. My period. Okay. I was assisting one of the lab members to design a tactile sensor for servers. Okay. This is a sensor prototype we have got. This is the truck performance. So this is cable. And we have got the sensor update here. This is the application code. Through the tactile sensor, you can tell this area has a stiffer, has a higher stiffness. This area has a lower stiffness, and then you can tell which area is active. Then this is the optical tactile sensor we have developed. We have a camera here. So this is on here. Yeah. And as a tape, we have several modules. So it is similar to what you have seen in Dresden's application. And here we arrange these modules, and we only use the camera to capture the changes of the light intensity for each one. Okay. And then we can display how these lights intensity is changed as a brick. That's what we call it a tactile array. So you have quite a few sensing elements. So here we have 3 by 4 sensing elements. And for each one you get the light intensity, and then you map the light intensity to the force you get. And here's how it works. So you have the light that travels through the optic fiber. So one fiber that sends the light in, and another fiber that sends the light out. And then you have these these mirrors to reflect the light. And if you have the contact force, this space will be changed, and the light intensity will be changed as well. And then you can map the light intensity to the force you get. Okay, so this is the key concept that we have got. And we have got these force pixel relationships. So it's kind of linear, and you can fit the light intensity to get the force. And we have also done some real-world experiments. Yeah? So this is the pig leaf we have got from the supermarkets. Yeah. And this is a nodule, a hard nodule embedded in this leaf. And then we use the sensor to palpate these different areas. And then this is the different intensity you can see. So here you can know region B give you higher stiffness because you can tell it from the lighting distance. And recently we have seen some research using optic fibers for surgical applications. This is not from our lab. Probably you were involved in this work. Yeah. So then we are back to 2025. So they are using optic fibers, and you can use the camera to image the contact with the soft tissue. So they have got extensive experiments on soft tissue assessment as well. Yeah. So you can check out this paper as well. But here, I would say the size is still large, and we want to further minimize the camera. And also the sensor, the whole sensor. So this is ongoing research in our. We are using this endoscopic camera. Yeah, so in the previous work, I believe they are not using the surgical camera. And here we are using this endoscopic camera, and we use a mirror design, so we can reflect the light. And we're using these optic fibers to further minimize the size of the sensor. Okay. And here is a 1 pound coin, and this is the sensor we have got. This is the sensing layer. So this design was inspired by Jocelyn, and so that you can minimize the size of the sensor. But the key elements are the same as the one we have seen. You have a reflector layer, you have got silicon layer, and you have got the supporting layer as well. But through our experiments, the miniaturization process is quite challenging. It took us a long time to try out the different sensors and also how to make the sensor elastic.
Can I ask a question? I'm very curious about the shape because have you basically asked the doctors whether they would prefer a shape that is flat, like here, or more complex shapes?
Mm-hmm. So our plan is to integrate our sensor to the surgical tools.
Uh-huh.
So we are talking to a doctor in the hospital.
Okay.
So this is the first prototype. This connected to the tool. And so that's why you can't see the surgical tool here. But in the future, our aim is to integrate the sensor into the surgical tool.
So as a part of the sort of these two fingers that take things.
Yes.
Okay, yeah.
So back to your question, so we want to maintain the shape, the morphology of the surgical tool.
Mhm.
So like you need to clean the vessels, so you have the surgical tube to hold the vessel.
Mhm.
So that's why they have such a shape at the tip of the surgical tools.
Okay, makes sense. Yeah.
We have done some initial results, and this is still ongoing research. So we have got some artery pattern. This is not real. This is just a photo. And we have got a testing platform. We attach a pulse sensor underneath, and we use our sensor to measure the deformation of the artery. So here is a simple task. It's just measuring the channel of the diameter artery. So the original diameter, D, and then we have the delta, and then we measure the deformation delta D over D. And again, we use convolutional neural network to predict the vessel's deformation. So here we are only predicting a single value, so how much it has deformed. And then we have got some initial results. So here you can see this deformation. We are feeding the raw data into the network, and then we predict how it has deformed. So this is the result we have got so far, and it can predict how much deformation you have got in the artery. Okay. I didn't expect it took so much time to arrive here. Okay. So I've put some chairs for the chair count. And I'll leave you guys to answer maybe. It can be a good topic for a Ph.D. The very first question we have got from our output paper is the materials. So all the tactile sensors is a layer of skin. Not only video-based tactile sensors, but also optical tactile sensors, capacitive or magnetic sensors. So you have a layer to convert the physical signals to electrical signals. Okay. So the material of the signal of the skin is very important. So if it's sensitive, if it's robust, if it can bear the wear and tear. However, I haven't seen any recent papers that conduct a full analysis of tactile skin materials in terms of sensitivity, flexibility, cost, and robustness. Interestingly, I have seen one paper from 1987. before I was born. Yeah. It was from Mark Kursky. So they have done some research to evaluate different materials as a skin for robotic fingers. They have tested rubber, they have tested some other materials, and they have got some insights. But for now, in the recent years, everyone knows material is very important for capacity. But I haven't seen any research papers or companies that open source their material analysis, how we can advance tactile sensing by improving such skins. There could be a good question to investigate through your Ph.D. Maybe Roland has a better answer to this.
I mean, there's two things to be said.
Yeah.
And one thing is that just the general idea of mechanics tells us if you want to test the softness of some material, your sensor needs to have a comparable softness, slightly stiffer. So the sensitivity depends on what you want to feel. There is not one material to feel all materials. So that's number one. And the second one is that the FDA is very slow in approving additional materials to be medical grade. And so we're limited in that sense to these Ecoflex and PDMS and stuff that has been around, which is, by the way, not less toxic. It just has been approved. And this is a process which is slow. And only labs that are very close collaboration to medical device companies can probably introduce new materials to the field, because only the companies know how to push the FDA towards approving new materials. So these are two constraints which I just wanted to put around this. But otherwise, I agree that this is not. I would probably put cost in brackets because there's very little material required. It doesn't matter how much it costs.
Okay. And also, from our own experience, when we fabricate such sensors, there are a lot of trial and error and manual processes. For example, the skin, you have to do molding, if you use 3D printers to print the elastomers, in the assembly process, it takes a lot of time and it takes a lot of effort. And you may not get the performance you want. Yeah? And also, I have seen so many cases, so in one lab, there's one sensor expert. That guy can make that elastomer, the other can't. Yeah? So the reason is that you have so many steps to make the elastomer or the whole sensor. And the dexterity in your fingers matter in the sensor fabrication. So that's why I'm thinking if it's possible to automate their fabrication so that you can make it more consistent and maintain the performance. Also, in my practice, I have only focused on vision-based sensing, but there are so many different construction approaches. Capacitive, magnetic, they offer different benefits. Okay. So to me, all of them have pros and cons. So maybe multimodal can be the future. And so you may integrate magnetic tactile sensing with very specific sensing. Okay. And low cost tactile sensors. Over the past days, I have heard a lot of discussions around the cost. Is that possible to get low cost tactile sensors?
I'll make a comment on this too, then that could be captured in one comment here. So you have the automation of the fabrication process and the cost of the tactile sensors. Some of this stuff is a little bit chicken and egg, where if there was a killer application that this is the problem, industrial problem to be solved, and we need to solve it, and all we have to do is make them a bit more low cost and automate the process of fabrication. That would be done. Like a large company would say, we will invest to do that. We will automate the process, and the price will essentially drop because it's a volume issue, right? But the problem is there's no killer application. We haven't found, everybody says Amazon, but we're like, yeah, maybe not. Like I don't know what the killer application is, but it's missing. So, some of those things are just issues of scale. It's like if the problem is to be solved, we will invest the money to solve it, and we'll find the processes that will enable the price of the sensor will drop. Like we were talking about this earlier, saying like a startup company. Let's say when Tactile started, you're selling dev kits for $7,000. It does not cost $7,000 to make a dev kit, I promise you. But you have to have a big markup because you're a very small company that needs to survive. And so a lot of small companies do that, where they sell at crazy high prices.
Yeah.
And also because there's no competition, so who else are you going to buy from? Like HDI Industrial Automation is the same. They sell their sensors for $10,000, but they don't cost $10,000 to make, but there's no competition really. So, sorry, I'm on a rant, but I just think that it's an issue of scale and necessity and so on. So I don't know that's on the research to solve those problems.
Yeah. It's not only research, but also so it's a question to industry as well. There are some other questions how to couple the transaction with software algorithms, we'll see later, and also the sensor networks across the robotic. So personally, I don't work on very much on body sensing sensor networks, but we perceive the sensor networks would be a key topic in the coming years, as you may have factor sensing for the fingers, you may have for the arm, or even for the torso. So the sensor networks will be also a key topic. Okay, and some participants told me the talks in the afternoon will be more challenging, and I can see that. So people get tired and it's getting warmer. So we have a little break. So in the next, I will cover simulation and processing. So first, I look for simulation. So we have talked about a lot of challenges for sensor fabrication. That's another reason why we started simulation for sensing. So we have seen gel size sensors, gel tip sensors, all different kinds of sensors, and this is a picture I have got from Fran in Paul. Yeah, so these are the elastomers we have destroyed through their experiments. Yeah. So all of these sensors, they come with software elastomer. Also not only field-based factor sensors, but also other factor sensors. So it's similar to our own skin. Yeah. So imagine your own skin, that is fragile. So if you apply a peel onto your skin, it will damage your skin. Yeah? But for us, our skin can grow, in fact. But for such soft elastomer, so how can we solve it? So you can solve them from the material perspective, as we discussed. But we came up with this idea to train the robot agents in simulation, so that you can reduce the wear and tear to such software elastomers. And you can train this agent and transfer such agents to the real world. So this is the same real to real learning we have done for tactile sensing. So we came up with this idea to simulate various tactile sensors around 2019. So at that time, all the methods we have seen, they are using FEM, finite element analysis, to simulate the software elastomers. But software elastomers are non-linear, they are very challenging to simulate, and they are computationally expensive. So if you want to get the tactile sensors with a software elastomer in the robotic simulations, it will slow it down, very slow. So one task can take like 40 minutes to complete. So that's why we came up this idea to go around simulation of software elastomers. So on the top, that's what you have seen. You have the camera, you have the elastomer, and you get the RGB tactile image. So that's the real world tactile image. So for simulation, so here we're not using one RGB camera, we're using a depth camera. And we removed the elastomer link. So there's no contact really happening here. But the depth camera can give you the depth map. So basically you map the shape of the object to this depth map. And then you can get the RGB image from the depth map by applying these RGB colors to your depth map. Okay. So from here, you get this height map from the depth map. Basically, you get these heights of the content. And then you can smoothen the height map. The reason is that for real world invitation, the contact edges, they are smooth. So you get this Gaussian filtering in nature in your skin. Okay. So that's why we get this Gaussian filtering for the contact edges to make it smoother. And then we get the contact normals at these contact areas. So with these normals, we get the illumination vectors, the light vectors, so that we know with these normals, we will get how much light for that area. Okay. So that's how we get RGB tactile image. So we are not really simulating the soft elastomer, but instead we are tricking, we are getting a trick to get RGB tactile image. And it can be fast, as we are not simulating the software elastomer information. Okay. So this is the very first experiment we have got. We replaced the tip of a 3D printer with a sensor. That's the real world on the left. So this is the gel site we have got. And this is a 3D printed object with a shape. Here you can see rectangle shape. And on the right, we have the simulation. So we recreated one 3D printer in the simulation. And then we attach the gel site sensor to the 3D printer in the simulation. And then we have one object, the plan. Okay. And this is the simulation result we have. So you can see it's quite rough, but it works. You get this contact area, and you know where you are contacting and how the lights are distributing in the tactile image. But there are quite a few issues that I will show you later. So these are the results we have got for the gel site sensor. On the top, we have the real samples from the real gel site sensors. And then this is the first version of the simulation that we have got. So we only use these contact areas. We didn't apply any filtering. So you can see the contact areas are quite rigid. And then we apply different versions of Gaussians, single Gaussian or difference of Gaussians, so that we can make the contact areas smoother. They look more similar to the real samples, especially for these areas. Yeah? By comparing the real samples and the simulation. And also we have proof it is transferable to different gradient distance sensors. All of these are gel site sensors. And this is the gel sling sensor. We can also simulate the gel sling sensor by tuning these color parameters. As I mentioned, there are some problems. So from the demo video, there are quite a few issues. In the real world is not perfect. So from here, when you get the contact, the artifacts of the object surface will be captured. This is the object that were the 3D printing. So you get the 3D printing artifacts on the surface. But the simulation is assumed perfect. It's perfect. There's no such textural artifacts on the surface. And also there are some other misalignments, so like the contact location in the real world. So definitely you get the calibration errors of the 3D printing, but in the simulation you assume it's perfect calibration. So that's how we come up with some solutions to address that. The very first solution we have got is very rough, is to get to manually create some textures. So these are the textures drawn by ourselves manually. So these circles, lines, dots to resemble the artifacts from the 3D printing process. And then we apply these textures to the depth maps. And then you get these artifacts in these services. Okay. And then when you do this downstream task, like object classification, so if you have such artifacts, you can largely improve the recognition performance. Okay. So before, for the sim to real, it was very low, around 40%, because of the gap between simulation and the real world. And then if you apply this texture augmentation, you can largely improve the recognition performance. So these are the objects we have created. So they are these basic geometric shapes to test our algorithms. So here we classify these objects. But by the way, so we have created these object sets and many papers in the recent years that are using these shapes. So it's easy to 3D print such objects in different labs, and then you can evaluate your simulation algorithm or other algorithms using these objects.
Shan, have you tried like sort of going beyond classification and perception into something that is more like behavior oriented? So favorite cloning or reinforcement.
Yeah, that's a good point. For this work, we didn't. We only took it as a perception problem, as we want to align with the data itself. But later on, I will show you some reinforcement learning.
Just a quick question. So other augmentations didn't work? Because I happened to like traditional RGB augmentations. They were not successful.
We did try some, so like translation, limitation of the image.
More at the pixel level.
Yeah, more of the pixel level. So we tried this augmentation methods, but you can see the main gap comes from the artifacts in the 3D printing process. So that's why applying this texture augmentation can improve the model. And then I will briefly show some other approaches we have developed to improve the simulation we have got. So one way is to through computational models. So here we use the generative adversarial networks to get these textures from the real world into the simulation data. So here you can see we get this simulation data and we know the content errors. And then we can learn these textures from the real world data. And then we inject these artifacts into the simulation data. So we call it adaptive data. And then this adaptive data will be more similar to the real data. And another work we have got is to not go around the software elastomer simulation. So here we have used these particle-based simulation approaches so that we can simulate this software elastomer and then we can get the deformation itself instead of going around it. So here are some results. So here you can see we use these particles and then we populate these motion vectors around these contact areas, and then we can get a more realistic contact deformation. But beyond that, we can also simulate tactile sensors of different morphologies. So for the previous works, we have seen the simulations of the gel cell sensors that are flat. Yeah? So they have the flat surface. But the gel tip sensors we have seen in the first section, you can see we have a curved surface. So it's more similar to our finger. So there are some new challenges when you simulate such sensors. The light travels differently. So for gel cell sensors, the light just be projected to the surface. But here, when you have the curved surfaces, you have the light will travel around the curved surface. So that's why we have experimented different light passes, like transport of these geodesic light passes. That is how light travels around our globe. Okay? And then we apply these geodesic light passes to our gel tip sensor. That's how we can mimic the light will travel, just in parallel to the surfaces of the sensor. Okay. And here is a quick demo to show the gel tip simulation. So you can see there's still some misalignment, especially for the contact locations. That's because for the 3D printer you have the calibration errors, and when you apply these contacts to make a different contact localization in the real world and in the simulation. And more recently, we have simplified all of these simulation methods. So here we are applying this multi-layer perception mapping so that we can directly map the contact shapes to the tactile images. So that is one way. We just use a network to map the contact shapes to the tactile image. Also, we have seen in the previous works the shadows cause some problems. So here we have developed some shadow generation functions so we can simulate such shadows in the tactile images as well. And then for the markers themselves, so we have simplified this problem by developing some mathematical models to simulate how they move in the tactile images.
You asked a question about the markers. This is something I've been sitting there thinking about. So you're trying to simulate for a reason, right? So normally it's for some sort of motor control, so you're trying to learn maybe by reinforcement learning how to control the robot based on some sensory input. And it's, yeah, you said the problem, it's very difficult to simulate elastomers and so on, so it's going to have a mark that takes it.
Yeah.
But why not go further? Instead of simulating the raw image, why not simulate the, say, marker output or whatever it is that the control algorithm is going to use? Because you're going to have a signal processing step in real pipeline. And so why not just jump over that as well and go straight from positions of objects in the simulation to what this process sensory input would be. It depends on your application. If you want to classify texture, you shouldn't do that. But if you want to do manipulation, that's probably what you want the control algorithm to have access to.
That's a very good point. So from our experience, the fidelity of simulations really depends on your applications. If it's for processing, you already need markers, definitely you can just simulate markers. But if your application is texture classification, you need very detailed of the images. So that's why we depend the image itself.
So here your goal was texture classification?
So here, for these works, our aim is to get a hub or platform of simulation. So you can use different functions of this simulation. It depends on your needs. if it's
What's your need?
so here we have texture classification. So it depends on the detail in the image. Also, it can be used for grasping. So we have selected different applications as a group. Yeah, so the aim of this one is to provide.
Now let's go for one example. How would grasping be supported by knowing the texture?
Mm-hmm.
How would grasping be supported by knowing the texture? I'm just trying to understand what.
So you mean in grasping, you don't need to know.
I don't know. I'm not a grasping expert. I'm asking as a layperson.
Yeah, that is true. That is very true. So when you do grasping, the marker motion or the force will be the most useful information you can. But what I want to say here is our aim is to develop a simulation that can be used by others. And this can be texture classification, it can be for grasping, so it depends on the users. So it's like we are developing software. And
No, I understand that. I'm just trying to understand who was using it at the end.
So it depends on the application. Yeah, so like the robotic researchers, they use the simulations for grasping.
Well,
So here shows some result to showcase the differences of our purchase and also the previous one. So this so the top ones are the real ones from the dataset. And then we have got the form models from our previous work, and also we have got the Tactile from our laboratory school. Yeah. And from our parts, you can see you have these different shadows that can simulate the ones in the real example. And then you can simulate the markers. This is an option. It depends on your need. If markers are what you need, so you can just simulate these markers, and then it can give you the false. And here is the result we have got for transferring the robot agents from simulation to the real world. And this is for the reinforcement learning for grasping. So you use these marker motions, and then you try and train the IR agents, and once you get this agent trained, you can transfer to the real world.
Can you talk more about this? So you have your model.
Mm-hmm.
Do I plug that into Isaac? Is that how? So I take your model, I put it into Isaac.
Mm-hmm.
I have Isaac to be my simulation backend and my train reinforcement learning in Isaac. Is that how we should think about this?
Yes. So this is it doesn't depend on the simulation platform. So you can use as a you can use Matrico, and this is a plugin, and then you can collect the data from the simulation environment, and then you can train the data. So this is to collect the data for training. And apart from simulation itself, we can also generate synthetic data from computational models. So we have seen this work for these generative adversarial networks to get these artifacts in the simulated images. And here we have also created this multi-switchable vision-based statistical system. So here it's not on simulation itself, but it's to generate data. So we have seen two main types of tactile data. So you get these markers, also you get these very detailed textures. So if your aim is to get the textures, so it would be better to not have the markers. But if your main aim is to have crusting, so the markers can give you more information like force, how the slip happens. So, but we usually only have one type of such sensors, either mark-based or markless-based. So this is the mark mode, so you have these markers. But also you can have the markerless, that you don't have any markers in your sensor. So our vision is that possible to put them together in one sensor. So for example, if you have this markerless sensor, is it possible to have markers in your data? Or the other way around, if you have a marker-based tactile sensor, is that possible to get better tactile image that you can see the texture in the tactile image? And then we have developed these computational models for these two transitions. So the first one, the left part, so you have the marker mode. You get the tactile images with markers. And then the aim is to remove such markers. And then fill these markers areas to get these textures. The other way around, you have the markerless mode. You don't have any markers. And then you apply these markers to explicitly show how the elastomer is moving, so that you can get a feeling of the force. So on left, we have this marker to markerless transition. So we use this diffusion model to fill these areas with the information around that areas. And then you can fill these holes, these marker holes. Okay. And then you can reconstruct this pseudo markerless image. For the other way around, you have the markerless tactile image, and you have this encoder-decoder network. And then you can apply these markers to show how much information it has for this point. So basically, you are applying this vector arrows to this tactile image. And then you have these different results, and we have got different results for the same indicators, and also we have tested how it can generalize to unseen indicators. And for this result, it can generalize to different indicators. And here are some demo videos. So here we have all these marker based tactile images, and then we use this generative method to generate these areas, and then you can get these results. So here I would like to highlight. So for other fields like computer vision or NLP, it's easy to get ground truths. For this problem, for the ground truths, we have to make a real markerless sensor, and then we have to make all the experiment setup the same as much as possible. And then we have got this markerless sensor through fabrication, and then we get the data, and then we compare them. Similarly, for this marker to markerless transition, we can generate these markerless images and this to compare these functions. And here are some results for this markerless to marker-based tactile image generation. I would say it still has a lot of noise. As you can see, the vectors are moving. But it shows it should be possible. So based on the markerless tactile image, so you can capture the information on the deformation, and then you can generate such marker-based image to give you more explicit information of contact. Then we have this table, so up to Stephen's point. So not only for simulations, but also for general tactile data collection, we have different representations. I would call it representations of different formats. We have tactile images, the raw tactile images. We have the depth maps. So that's intermediate output from our simulation. As I mentioned, you can use a depth map. You can use a depth sensor to get this depth map. Yeah. And you can also use only motion of the markers as your repetition, your data. Or you can use force or torque. But they have pros and cons. If your aim is to maintain a very detailed information in the tactile images, and you want to reduce the gaps between simulation and the real world, so tactile images are what you want. So it can maintain very rich information, texture, force, sleep, as this is in the same format as the real data. But the cons, they have very large simple row gaps. As we have seen, there are a lot of factors that affect your simulation results. If you use the intermediate representations, like the tabs, so there's some work like from Mason and the Proras group, they just use depth maps for simulation. And then you train your agent, and then you can transfer to the real world. So it will give you smaller simple row gaps while maintaining some essential contact information. But you will lose the high resolution of contact agents compared to the tactile images. So similarly, if you use markers, so it's sufficient for grasping and manipulation tasks, but it's less informative when surface texture is the feature to investigate. Similar for force torque, so it can be very useful in industrial application, but usually you need physics-based simulation. For example, fundamental element analysis. So here are some pairs. So there's demo, as you can see from the table. There's demo in tactile sensor simulations, so you need to make some trade-offs to efficiency and accuracy. Yeah. So the depth maps or marker motions can be more efficient, as it can give you less data to transfer. But the tactile images, more realistic tactile images, can give you more accurate representations. And then here, the simulation is a very active field in tactile sensing. My question to the field or to you, are highly accurate simulations necessary? And so, like Stephen mentioned, if your aim is to do grasping, probably you don't need very realistic simulation.
I'm curious about, maybe this is just pure ignorance because I haven't done this, but I understand a bit about simulating the tactile input, but how do you simulate the interaction of the physics between the contact mechanics between the object and this, it's meant to be a soft gripper, you're saying, just take away the skin. For example, if the object makes contact on your simulated surface and pulls to the side, there's going to be a stretching of the skin and a lateral force will be generated. And so, does Mijoku simulate some simplified version of contact mechanics, or how do you handle it?
We have tried. That's another problem, as that's the interaction between the sensor and the object. I would say that's more challenging, especially for the shared force involved in the interaction. So from our experience, it's very challenging to tune such patterns. We have tried to do as example, but still the soft contact, so still very challenging to simulate. I will show you some results later for such.
That part's really interesting, and the history of the contact, because if you make contact somewhere and move across, if you just look at the position the last time, it just looks like an indentation. But that's not true. You make contact here, and it's stretched, the skin kind of over. And so I was wondering how that aspect is captured in cinema. And you say it's hard.
Yeah. I can see there are many researchers working on the simulations of the world itself. As the interaction, more like the world, how one object interact with another object. So we have seen Epic Demo is the one developed by NVIDIA, but still we have tried many of them and not very realistic. At least the ones we have tried so far.
Yeah, my personal view, which you should take credence in, is just that I don't think the simulation approach is the right way. I'm not saying your work, right? I just mean generally for training robots to do stuff. I think it's been okay for reason body. My feeling is that when it gets into soft mechanics, I don't know if the simulators are there.
Yeah. There's one.
Yeah.
Well, they work pretty well.
Do you? The soft body interactions, like with, say we had like elastomer or tactile sensors and we're manipulating the soft objects or flexible objects.
Yeah, but tomorrow I'll choose some of the real caliber.
Perfect.
Yeah.
That'd be put in the place.
But I think you're right though, like I think there are some things that are easier to simulate and to transfer better than some other things. Like organ stuff doesn't transfer very well. Organ stuff, so things that are like a 3D volumetric, the whole thing, are rougher than like fabric. Fabric is a little bit easier, cables are a little bit easier, elastomer looking things are not so terrible.
So maybe I'll keep the some questions for
There's one simulator called SOFA for software robotics simulation. So some of our collaborators use SOFA for self-interaction, but they're quite slow, similar to these other elements analysis software. Yeah, but probably you can do better.
I think the best work in that domain is from Tucker Hermans. He's at Utah. He's pretty famous for working with interface domain. Surgical robotics, soft robotics. He also works at NVIDIA. And he works a lot on simulating those things. He's like,
The second question is probably related to the question of how highly accurate simulators is necessary. And the question is about the policy that you showed. So you also try with simpler simulators, because I feel that it's not really necessary to have such a precise simulator for inserting packs. And the other one is, since dynamics is really important, it's also tested on more difficult, in more difficult scenarios. Or not like just handling flat surfaces, but like more complicated surfaces. These are my two questions.
Yeah. It really depends on your application. Yeah. But from our end, so if you have a very realistic simulation, you can pick up what you need. Yeah. So if it's realistic, so you can have realistic technologies, or you can have intermediate outputs.
Shan, we're I think a little bit over time. Do you know how long you will need for this third part?
I think most 10 minutes.
Perfect.
Then I will introduce some of the representation learning. So as I mentioned at the beginning, we work on robot perception, not only on touch but also vision as well. So we have been working on the stereo tactile integration. So this was the very first one we got for vision tactile sensitive. So here we use fabrics. So we have called 100 pieces of fabrics, and we collected digital images of these fabrics. Also, we have collected the just data from pressing the sensor against the fabrics. And in that work, we use these common networks to extract information from vision data and just data, and then we use this covariance analysis to maximize the correlations between vision and presence, so that we can enhance the perception for robots. From there, we have also got cross-modality. So here we have this touching to see and seeing to touch. So this is the same data set we have got. We got the tactile input, and then we generate this visual output. And the other way around, we have the visual input, and we generate the tactile output. So we have got some experiments, and we have seen if it's the fabric is textureless, or this color is not very variant, so it can work well. But definitely you have a very much different if you have very much color variance in the fabric, and it won't work well to transfer from vision to tactile. And so these are the networks we have developed so that it's basically a generative anniversary networks that you can transfer from one domain to another domain. So these are the results I have seen. So for this plan color fabrics, they can work well, but these are the failure cases if you have very much color variance. So the tactile data you generate will be very bad. So that's why. That's because you have the difference in these two So have also got some possible triggers for you guys. So we have seen this data collected from simulation from the real world, but we haven't seen very much on benchmark. The board has started this initiative. I think this is a very important topic in the coming years. Not only benchmarking the data itself, but also benchmarking the sensors. And what are the suitable evaluation metrics for benchmarking tactile robotics? So in the previous slides, already have seen different metrics. So for the practical level, you have accuracy. But for the physical level, you have force, you have slip, and also for the image level, you have structural similarity, you have PSNL, the signal-based metrics. But I haven't seen any papers to evaluate evaluation metrics. I think that's missing in our field. So force can be a good representation of metric measure to evaluate your sensors, but it may not be the good one for some specific applications. And then we have seen the recent development of neural networks for tactile data, but they are mostly centralized. So you collect the data, you process the data on your server or your computer, but tactile sensing is distributed across the board. So we really need the local tactile processing unit that can process the data locally. And also how to use liquid data while improving visualization and learning. So compared to vision, compared to tests, tactile data is relatively small. So how to leverage limited data while maintaining the performance. And foundation model. So it is a foundation model needed for reporting tactile perception, especially if you use different tactile sensors. Okay. And also for vision and tactile sensing, the most common ones we have seen is to concatenate the features from visual and tactile in this visual tactile fusion. But that's not what we do in humans. And definitely there should be better ways to fuse the visual information and tactile information. Okay. My last bit, I don't touch very much on actions, but I will show one of our works on actions. One of the topics we have been working on is to use tactile sensing, and possibly with vision as well, to handle deformable objects. We have seen deformable objects are very dynamic, they are changing their states dynamically. So this is one example. We use a Umi robot to like this cable. And then this is the simulation we have got for the cable for the software accuracy. Okay. And so we started this program using multimodality, completed the task of following these informal linear objects. And we have these challenges, their shape change, and also they may have different problems. Cable, rope, and most of them they use digital constraints. So for example, an object is on the table. So we train these IL agents in simulated environments. So this is desired by environments can be on to extensive number of episodes. So like what do we have seen before. But then we have these new challenges, sliding and realistic grasping. So in this work we have to tune many of these parameters in simulation, like friction, coefficient, between the gripper and the software object. And then we have got this reward function so that we can define the problem so that the robot can follow this object from one end to another end. We have defined a reward for moving forwards, towards the end, and also reward for being close to the end. And that is penalty for dropping the object, and also we have the number of particles being held in the grip. So basically, to design these reward functions tailored to this problem. So here, in the methodology, we have different types of inputs. We have the real input from the top view camera, and then we have the kinematic input, and we have the tactile input from the grippers. And here, we didn't use any simulated data sensors. So it's fully assumed we have theta and y, these two variables, to give the tactile information. And then we feed this information into the IR policy. And then we have collected a lot of data, so different successful trials and also the failure trials. And we have defined these evaluation values. So how much time it stays on the table, and if it will drop before reaching the end. And then in the experiment, I wanted to highlight these experiments were already done in simulation. We haven't been verified in the real world yet, but from our experiments, we have seen that for most of the time, vision can give you the most useful information. It can capture the global states of your cable. But if you apply tactile sensing, it can know the local states in the paper. And then you can further improve the success rate from something 2% to 92% when you leverage all the signals. So this is the last part of triggers. There's another field called active touch. So how to combine tactile control with active touch. So based on the information you have collected in your experience, how to improve your information gain or your probabilities of success in the next steps. I think that would be a good research topic to follow. And also, how should tactile robots actively learn from its own experience? So, for example, long horizon learning. Okay. So to wrap up my talk, so we have seen sensing, perception, and actions for tactile robotics. We have developed vision-based tactile sensors for perception and manipulation tasks across different skills. We have also developed simulations and also repetition learning, reinforcement learning with vision and tactile data. So we are still working on quite a few challenges. So some of them, so tactile sensing can go beyond centimeters. It can go to millimeters or nanometers or meters to different scales. Also, we would like to reduce the center-root gaps for tactile simulations, and also we would like to develop data-driven approaches for tactile learning and active learning that can help for control and tactile education. So these are the report from me. Thank you very much.
We have time maybe for 2 questions.
You mentioned in your simulations that shadows are simulations that tactile images that you need to account for shadows cast by objects along the other part of the image. Do you consider inner reflections, and have you found inner reflections between objects or between like the folds of objects to be a problem when you're trying to do simulation? And do you take into account inner reflections?
So you mean the shadows
So if you,
in the sensor itself? Or?
I'm talking about, so if you indent 2 objects, you're going to have inner reflections between the two objects that will modify the sensor output reading. So, so I was just curious if you consider, take into account, or have plans to take into account inner reflections as well, and whether you think they're important at all.
Okay. Yeah. So in our work so far, we haven't considered these internal reflections of these 2 objects. I think if you have multiple objects, so that will be meaningful to investigate, with the presence. So with the tactile output, so you can infer how these 2 objects interact with each other.
Thank you.
All right, then let's suspend here. Thank you again, Shan.